Yeah, I think I'll start. The rest of the people will join as I introduce. So welcome to the 1W-MINDS seminar. I'm extremely happy to have Dan Spielman speak today in our seminar. Dan is of course, as I'm sure all of you know, extremely distinguished. If you go on his page, you can see the long list of awards. He has a lot of the top awards, not only in the field, but in all fields. He's a MacArthur Fellow, he has an Evan Lehner Prize. He has not only a Gödel Prize, but 2 Gödel Prizes. I personally like a lot of his work, and you probably know a lot of his work on smooth analysis, on linear Laplacian solvers, on sparsifiers. I personally really like his really beautiful solution of the Kestensinger problem. And if you haven't yet, I highly recommend going to his page and take a look at his spectral graph theory lecture notes. They are some of the best lecture notes I've ever read. And on top of all of this, and perhaps the quality that I most enjoy is he gives amazing talks. So if you haven't yet had the pleasure of listening to him, you're in for a treat. Then please, the floor is yours.
Okay, thank you very much for the introduction, Alfonso, and thanks for inviting me. I will say, and again to the panelists, other people there, I speak more eloquently when I have an audience. So just, like when I'm practicing in my hotel room somewhere to talk, I can't put a sentence together. So I'm going to keep trying to look at the panelists, and that hopefully looking at them will help me speak. I don't know why this is, I just know that it's true. So today I'm going to tell you about work that we just submitted and appears on arXiv in a paper called Balancing Covariates in Randomized Experiments Using the Gram-Schmidt Walk. It's joint work with Chris Harshaw, who's a graduate student working with me, Frederick Savje, who's a professor of political science at Yale and an expert in experimental design, and Peng Zhang, who's a postdoc working with me. The Gram-Schmidt Walk algorithm, which I'm going to refer to often, is not ours. That comes from a paper called The Gram-Schmidt Walk, A Cure for the Banachik Blues by Bansal, Dadush, Garg, and Lovett. So they introduced this algorithm to solve a problem in discrepancy theory. Discrepancy theory is mostly about, given a bunch of things like vectors, how do I divide them into 2 groups that are similar? And you would imagine this is something you want to do, say if you're testing the effectiveness of a medication. You want your control group and your treatment group to look similar in many ways. You'd like the populations in both groups to be similar, and that's just the sort of thing that discrepancy theory is built for. But we also know that's not enough. We know that you need, we call these things randomized controlled trials because there's randomization in them. And what I'm going to do, by the way, to show you, I know a fair amount about discrepancy theory, not much about experimental design or randomized controlled trials. I've been learning. So Frederick is usually my go-to expert for this, and Chris has become an expert. But if you have questions on it, I'll still try to answer them. Okay, so what we need to do is we need to marry discrepancy theory with experimental design. And that's what this talk is really about. And that is really what this Gram-Schmidt Walk algorithm enables us to do. So the outline of the talk is I'll begin by telling you about randomized controlled trials and how we design them and the sort of things we want to measure, like average treatment effects and how we get confidence intervals from tail bounds. Then I'll tell you about the Gram-Schmidt Walk algorithm, the sort of output guarantees it has, how we can use it to design randomized controlled trials. I'll get to tell you, I think, a little bit about how the algorithm works, a little bit about the analysis, tell about how we get confidence intervals out, which is what a lot of experimentalists really want, and finally tell you about some of the problems that remain open, although you will think of many, many others. Let me just say, there are a huge number of open problems in this area, most of them, as far as I can tell, not even identified. Everywhere you look, you will find them. Okay, so let's imagine a randomized controlled trial. I know everyone today is thinking about testing effectiveness of vaccines, but let's imagine maybe less high stakes one, testing educational methodologies. Let's say we want to compare a regular classroom to a flipped classroom. So we'll imagine a professor who's trying to tell a bunch of students that 1 times 1 is equal to 1. And we want to figure out whether or not that goes better in a flipped classroom than in an ordinary classroom. And let's imagine for now that we have a bunch of experimental subjects, and on first inspection, they all look identical. So what we do is we assign some to the control group and some to the treatment group. And we call this a randomized controlled trial because we're doing it at random. And I'd like to take a little bit of time to explain to you why we really want to do this at random and what we get from it. And I'd say what sort of random do we mean here? It doesn't have to be uniform. Well, first, what do? We measure outcomes, which in this case, I will think of as whether or not the student understood the concept. So if I draw 1 in their head, that means they understood that 1 times 1 is equal to 1. If I put a question mark there, it means they didn't get it. And usually what you do after you do this experiment is you take a look at the average outcome. Like we can look at the control group. There was only 1 student who understood. In the treatment group, there were 3 who understood. This leads us to expect that the treatment was successful, especially if the assignment was random, not just like, the more advanced students were put in this class. That would be bad. The model under which we're going to analyze these sorts of experiments is called the Nyman-Rubin potential outcomes model. And what we imagine in this model is that for each subject, there are 2 potential outcomes. I drew them here on the top of their head and in the bottom. One outcome at top is what happens if they're assigned to the regular classroom. So if this subject is assigned to the regular classroom, then that person gets the idea. On the bottom, we show what will happen if this person is assigned to the control group, the flipped classroom. If they're assigned to the flipped classroom, they don't get it. In the potential outcomes framework, we imagine that these potential outcomes are fixed in advance. That means that the only thing that's random in this whole process is the assignment to treatment or control. So at the end of a study, when you want to say, I think this is the treatment effect, and the probability it's due to chance, or the standard deviation on my estimate is something or other. When you talk about a standard deviation, you're talking about something random. The randomness comes from the assignment. Now, I should contrast this with another model that you might have in mind. You might have in mind a model where someone's response to treatment is random. Like you might imagine that for this subject, whether or not they learn the concept in the control, let's say you might imagine they learn it with probability 70%. You're welcome to use such a model if you like, but if you do, I just ask you to sample the random variable before we begin this analysis. So you can imagine sample up top whether or not they're going to respond to treatment, sample down bottom whether or not they'll respond to control, and then fix all of those things. The reason I want to do that is because this makes fewer assumptions. And one of the things we really want to do in this area is understand under what assumptions are our analyses valid. And in this case, I want to do that only under the assumptions that I can control, which is this assignment. I don't know if there's some like randomized data generation process that goes on in people's heads for whether or not they'll respond to treatment or control. Okay, the difficulty in randomized controlled trials, I should say, it comes from what we really want to know. I really want to know not what is the outcome, but what is the likely outcome. Like I want to know, on average, are there more 1s in the control group or are there more 1s in the test group? But I don't get to know that. All I get to see is this random sample. So the key problem here, which I draw this way, is that you never get to observe both outcomes. For each individual, you only get to see the potential treatment or the potential outcome that they correspond to the group to which they're assigned. So this poses a big problem. We can't see both potential outcomes. We just have to use this sort of sampling process to estimate what's going on. The problem becomes more interesting once the subjects are not identical and we know something about them. And what we know something about them, I've learned, are called covariates. Covariates are information we have about the experimental subjects. So here I drew some of the ways in which the experimental subjects may differ. The most prominent one is that some of them are gray heads, sort of old, and some are newborns. Okay, you could imagine these covariates are correlated with how well these subjects will respond to treatment. And you might be nervous that I put 3 newborns in the control group. And if you look at the potential outcomes, Well, all of the older people understood the concept that 1 times 1 is equal to 1, really probably before we even began this experiment. And all the newborns have no idea what's going on. Okay, so what do we do about this? How do we think about this? Well, first, let me reveal the picture that I just described to you. Here were the potential outcomes I was imagining. I was imagining that the potential outcomes really just corresponded to how many gray hairs someone had on their head. Or in the case of this one, who looks more like me, maybe at one time had. We're assuming the potential outcomes are correlated with age perfectly. So there is nothing wrong with the design of our experiment. A random assignment still works on average. It's just that, unfortunately, what's happening here is that a random assignment, or what we're measuring at the end, is just how many newborns were assigned to control and how many were assigned to treatment. We're not really measuring anything particular about the effectiveness of the intervention. That's actually good. It means that if I have enough people here, the number of newborns assigned to each group will be roughly the same, and we will conclude that the intervention has no effect. And here it doesn't. There is no difference between control and treatment. It just depends on whether or not people are old or young. But it means we can improve our experiment. If you think that something like age might be correlated with how people respond to treatment, then you should try to make sure that there are the same number of old people in the control group and the treatment group. Here I give an example of just 2 units, 2 subjects, so I flip which groups they're assigned to. Now I have the same number of old people in both groups. That seems like the sort of thing you want to do. And this is one of the sorts of things people try to do in the field of experimental design. They try to balance the covariates between the 2 groups to make the 2 groups look similar. If you just have a few categories, like gender, or old, or young, or having some condition or not, you can do this. It gets more complicated when you have widely varying covariates. Your experimental subjects can differ a lot. Then it is not as clear how you should assign people to treatment and control, and that's really what this talk is about. So just to give you an idea of the sort of things you might have in mind, first, covariates don't have to be binary. They could be continuous, like age. Like age is actually a really important one to balance in medical trials, especially if you're looking at longitudinal studies, because for better or worse, the older people are, the less time we expect they have left to live. So you want to make sure that the age distribution between treatment and control groups is the same, not just binary categories. Sometimes your covariates are pretty high dimensional. A lot of statistics is designed for things like 4 or 5 dimensional. And then you can talk about things being asymptotic, but 10, 40 dimensional is quite common. And if you're looking at things like genomic data, then the dimensionality of your covariates is much more than the number of people. I will tell you just up front that I don't know what to do with the genomic data case yet. What I'm thinking about really only works still when the dimensionality of the covariates is less than the number of subjects. But that's still going to free us up a lot. Now let me be a little more formal. I want to remind you again, in the model we're considering, the assignment is the only source of randomness, and the response to treatment is fixed. For today, we're going to consider assigning subjects to one of 2 groups, either a test group, like treatment, or control. There are 2 potential outcomes for each subject. We observe little a of I if we put subject I in group A, and little b of I if we put subject I in group B, but we can't observe both. When we talk about experimental designs, what we are talking about is the distribution of the groups A and B. So literally, when I talk about an experimental design, I mean, how am I going to decide who to assign to the control group? So here are some standard designs I just want to mention. These are the classics. First, uniform. Just each subject, put them in group A with probability a half, independently. That's the easiest thing to think about. It does have the downside that the 2 groups might have different sizes. Well, I'll admit it's not a priori clear that's a downside. We'll investigate that in a bit. Okay, you could do balanced. You could let A be a uniformly random chosen subset of half of the subjects. That's sort of the thing that probably first comes to mind, and that's what I was implying on the initial slides. Finally, a common way to handle, especially low-dimensional covariates, is matching. Here what you do is you try to pair up subjects so that they look similar. Like ideally, you try to make pairs that are similar in all categories. And I think of this as making a matching in a graph where the nodes are the subjects and the pairings are the edges. And then for each pair I, j, you flip a coin. Either you assign I to group A or j to group B, or I to group B and j to group A, each with probability a half. That's like one of the standard workhorses of the field. So all of these designs and the designs that I'm going to talk about today have one very useful property. It'll simplify everything. For each element, each subject, the probability there in group A is a half. We're going to only consider designs like that. But let me emphasize, even though for each subject, the probability there in group A is a half, these are not going to be independent in general. Really, there's only one design in which those choices are all independent. What we're going to discuss measuring today is the average treatment effect, often abbreviated ATE or 8. We're going to denote it by tau. So that is the sum over subjects of the potential outcome if they're in the treatment group minus the potential outcome if they're in the control group. Well, times 1 and n to make it the average treatment effect. Of course, the difficulty is we can't actually measure this because for no I do we ever observe A of I and B of I. So instead, we're going to estimate it. And our estimator we'll call tau hat is one of the two you would naturally think of for this problem. It's the sum over I and A of the value A of I minus sum of I and B of B of I times 2 over n, where 2 is the right normalizing constant. And for those who aren't used to this, let me just tell you, this is usually called a Horvitz-Thompson estimator. I know putting this terminology on it is overkill, but I'm going to mention it now because we're going to use it more later. The idea is if you want to estimate a sum of random variables, but you don't get to observe all of them, what you do is when you do observe them, you normalize by multiplying by 1 over the probability you expected to see that variable. In that case, you get your estimator right in expectation. So if we want to estimate tau, which is the sum of the AIs minus the BIs times 1 and n, we sum, say, the AIs that we observe divided by a half, which is the probability we see AI, minus the sum of the BIs divided by the probability we observe BI, that gets the constant right out front. If we do this right, our estimator is correct in expectation, which I'll admit is a low bar, but it's a good start. I just want to mention one estimator, the other estimator that would occur to you that we are not using today. That is the difference of means. So this is a very natural thing to do. You would take the mean of A of I over the I's in group A and the mean of B of I over the I's in group B. It's a natural estimator. There are a lot of reasons to want to use it. The reason I'm not going to is actually it might not satisfy this. It can be biased. And the variance can be very difficult to reason about. So while I suspect it is usually a good estimator, I can't say that. I'm not sure what to say about it yet. Okay, so as I said, we get the expectation right using this estimator. But what you really care about is not just getting the expectation right. You want to know how close is your estimator to the correct average treatment effect. That is, like, what is the probability that tau hat minus tau is more than some number lambda? What are the tails? Well, the first way to get at this is to think about the variance. And I'll give you a nice formula for variances here. You want to understand the variance of tau hat minus tau. And to simplify things, let me recall that since tau is the expectation of tau hat, that's just the variance of tau hat, and that's the expectation of the square of tau hat minus tau. Once you get the variance, you can use Chebyshev's inequality to reason about the tails. And that, again, is a good start, but we often want more. We want things like normal random variables. And the way we're going to get at this is through the language of sub-Gaussian random variables. Now, there are multiple definitions. I can think of at least 4 of what it means for a variable to be sub-Gaussian. So let me tell you the one we're going to use. we will say that tau hat is sigma sub Gaussian if, well, the formula says that if the exponential moment generating function is dominated by the exponential moment generating function for a Gaussian variance sigma squared. That is, for all lambda, you want that the expectation of the exponential of lambda times the difference is the most the exponential of sigma squared lambda squared over 2. If you're not used to working like this, let me make you a little happier with it. If you recall how you, at least how I first learned to prove like Chernoff bounds and Hufting's bounds, it was actually looking at this, and then we used Markov's inequality to bound the tails. And when you use Markov's inequality, it tells you the probability that tau hat minus tau or error is more than lambda is at most something that is exponentially small with lambda. And I just want to mention, this is a bound that I have always been very happy with until I started talking to people in experimental design. Because when they look at this, they say, you know, this is sort of right in the large first order term. But if you take a look at the error function, there is a second order term that should be here. You multiply by it, and it actually makes your confidence intervals appreciably smaller. And we're missing that. That is one of the things I would love to fix about this work, honestly, because people care a lot about the accuracy of their estimators in this business. Here's one way of thinking about why so much. If I'm losing a factor of 2 in my confidence interval, you're losing a factor of 4 in the number of experimental subjects you need in your study. And the most valuable resource in things like medical trials or almost anything else really is experimental subjects. You want to do your studies with as few as possible. So one of the questions, and I'll remind you later, is to see, can we reproduce any of this work using a somewhat sharper notion of what it means to be sub-Gaussian, because this is missing a term. Okay, let me now work through what the variance is, what the error is, and what all these terms look like. So first, let's make it a little more algebraic. I will choose a vector z, which is a random plus minus 1 vector, which is 1 for the entries I and A and minus 1 for the entries in B. We're going to use z to write the error of our estimator. I'll multiply by n. So n times tau hat minus tau turns out to be z transpose times, or the inner product of z with the vector A plus B, where I remind you A and B were the potential outcomes. So we're really summing them. I'm going to use this A plus B vector a lot, so I'm going to call it mu. I put down a derivation of this fact, which might look a little silly to put down. Just the reason I did it is many people have the intuition that I should be looking at A minus B, but I assure you it really is A plus B. This will be the error in our estimator. So this enables us to get at the variance. And I will tell you how to compute the variance now for any design. So the variance of tau hat is 1 over n squared, which I'll usually ignore, times the expectation of z transpose mu squared. So take that square, write it as mu transpose z times z transpose mu, and then combine these terms into the middle. And you see what we've really got is a quadratic form. In vector mu, and matrix in the middle I call z, which is the expectation of this little z times its transpose. And I remind you, z is a column vector, so this is a matrix. The key point here is when I specify my design, once I specified my design, I know capital Z, but I don't know mu. So my goal is to try to make sure this is as small as possible without making assumptions about mu. So let's see what happens in the IID case.
Wait, sorry, Dan. Let me do. What can you remind us what mu is?
Oh,
mu is the
A plus B. So oddly, it is the sum of the potential.
Okay, got it. Okay.
Subject I is in group A plus in B.
I see. Okay, thanks.
All right, so it's, you could call it the sum of the potential outcome vectors. Okay, so let's take a look at the IID case. If Z is each entry plus or minus 1 independently, I want to look at the sum of the outer products. The ijth entry of the expected outer product is just the expectation of Z of I times Z of J. Okay, Z is a plus minus 1 random variable, so the diagonal terms here, when I is equal to J, they're going to be 1. And if the terms are independent for I different from J, then the off-diagonal terms are 0, and Z is just the identity matrix. So that means that the variance of tau hat, our estimator, is 1 over n squared times the norm squared of mu. That's a very clean formula. And it actually means that in some sense, the IID design is optimal. Let me explain what I mean. If you give me any design, the diagonals here of Z are going to be 1. So the trace of the matrix Z for any design always is n. It means that Z has to have some eigenvalue that's 1. Or here I wrote the norm, but it's symmetric. We can talk about the eigenvalues. It means that there always exists some sum of potential outcome vectors mu for which the variance would be at least the norm of mu squared. So if you don't know anything about mu, and you want to make an assumption that it's worst case, whatever design you use, like there will always be, it will be dominated by the IID case. For any design you use, there is some mu for which your variance is larger in your design, or at least as large as it is in the IID case. So IID is optimal. So why am I giving this talk? Well, if you want to get better performance, you need to assume something about mu. And just what we want to do is we want to do this in such a way, so if our assumptions are wrong, we don't want to lose too much. Let me say, like, I want to get better, more accurate estimators if I can make some assumptions about the potential outcomes, maybe that they're correlated with covariates, but I don't want to lose much if my assumptions are wrong. And this says you have to lose something. Just the question is how much. So let's take a look now why you might want a random balance design, because I just told you the other one is optimal. So really think about taking a uniform plus minus 1 vector Z such that the sum of the entries in Z is 0. You can compute the vector capital Z, I mean the matrix capital Z here. There's a leading term of n over n minus 1, let me just, that's more than 1, times the identity, minus 1 and n times the all ones matrix. By the way, this is one of my favorite matrices. It's a multiple of the Laplacian of the complete graph. But we're not going to use that fact, but for those who are used to thinking about it, it helps. Here's what this tells us about the variance of the estimator. There's a leading term, which is 1 over n minus 1 squared. That's a little larger than 1 and n squared. But inside, instead of the norm of mu squared, I have the norm of mu minus the average entry in mu. And that can be smaller than mu, at least if the mean of mu is small from 0. And that happens sometimes. Like imagine all of my potential outcomes are positive. If all the potential outcomes are positive, well, then the mean of mu will be bigger than 0. And if they're strongly positive, you know, it's probably significantly more than 0, this typically will have a smaller norm than mu. So that's one of the reasons you would want to use a balanced design. If you were assuming that your potential outcomes were positive, you are not normalizing them in any way. I mean, maybe you should, but if you were not, then a balanced design can do better than the IID case. But now let's see how we use covariates. So for my covariates, I'll represent as vectors in RD. So for each subject, we have a vector in RD, and we're going to assemble them into a matrix we call capital X. The covariates will be particularly useful if mu, which is all dependent on the potential outcomes, is close to the row span of X. So to explain why, let me begin with the ideal case. The ideal case is where mu, let's say, is actually in the row span of X. So that means I can actually write mu as X transpose times beta. Well, now I get a nice expression for the variance. Instead of talking about the norm of mu, my expression for the variance, it's a quadratic form with the vector beta in this matrix, which is xz x transpose. Now, if I don't know beta, and I want to assume that this sum of the potential outcome vectors mu is in the row span of my covariates, well, I'm going to try to make the norm of this matrix small. I guess I'll tell you all in advance that it's going to be at most 1, but we'll get there in a minute. The reason I mention that now is we should also actually make sure this looks like a win. And to do that, we need to know something about the norm of this vector beta squared. So, well, we're not going to, but let me at least tell you one ideal case to have in mind. what again, in this ideal case that mu is equal to x transpose beta, imagine that each of these vectors xi has norm 1, and that the rows of x are orthogonal. If you were in that regime, then when I take a look at x times x transpose, it's a d-dimensional matrix. It's n over d times the identity. If we're in that regime, this enables us to relate the norm of mu to the norm of beta. And we get that the norm of beta squared is d over n times the norm of mu squared. Okay, so if d is much less than n, then the norm of beta is much smaller than the norm of mu. And in this case, we'd like terms that depend on the norm of beta squared, as opposed to the norm of mu squared. This is exactly, in some sense, what the Gram-Schmidt walk is for. So the Gram-Schmidt walk of Bansal, Dadush, Garg, and Lovett, it gives us a distribution on plus minus 1 vector z for which the norm of this matrix is small. So to explain it, let me expand out this again. This matrix xz x transpose is really the expectation over z, which is our plus minus 1 vector, of xz times the outer product of xz with this transpose. So think of xz, really what it is you're taking the covariate vectors and you're summing them up with plus or minus 1 signs. So I should go back to this picture here, right? Like if I multiply a z here, then I'm summing these with like plus 1 or minus 1 signs. We want that sum to have small, well, variance, I guess, here. Okay, so here's what they do. Given vectors xi, with a guarantee that they all have norm at most 1, they sample a vector z so that this expectation, that is the operator norm or largest eigenvalue of the expected outer products of xz with themselves, is at most some constant sigma squared. And actually, well, they don't state that result explicitly because they're going for a bigger fish. It's a consequence of their bigger result, which is that xz is a sigma sub-Gaussian random vector. Or what they mean for a random vector to be sub-Gaussian is you take the inner product with any fixed vector, and that's a sub-Gaussian random variable. Or more concretely, you give me any fixed vector theta. The expectation of the exponential of the inner product of theta with xz is supposed to be at most this exponential, and that corresponds to being sub-Gaussian. And the reason they did this is because, well, there was this resultant discrepancy theory due to Banachek, which I won't go into the details, but it was proved in '98. It was just an existence result. It told us that some nice divisions of vectors existed, but there was no algorithm for it. An earlier paper of Dadush, Garg, Lovett, and Nikolov proved that if you could sample vectors with these properties, then that would enable you to make Banachek's theorem algorithmic. And that's what this paper did. So in particular, they just needed some constant here. I don't think they particularly cared what constant they got. They did give us root 40. I want to mention we cared a lot about what constant you got, and I will show you why. So most of our paper is actually devoted to an improved analysis of their paper, showing you that you can actually get sigma equal 1 here. So this is going to be 1 sub-Gaussian, this matrix will have norm 1, and that's optimal. You can't improve on that. And I will give you just a hint of how that analysis happened later. Maybe the main thing I should say is their analysis comes down to looking at a Martingale, and they use Friedman's inequality. And we needed to come up with something very different than that because Friedman, you lose something. Like you're not going to get the optimal analysis using that. And our analysis, at least I've never seen anything like it before, but we haven't figured out any clean way to describe the technique or put a name on it. But if some of you happen to look at the paper, if you've seen it before, please let us know. And if not, hey, if you can think of a great way to describe it, that would be very helpful. Okay, but first, let's see what this gives us. And I'll begin with taking a look at variance. But now let's not be in the ideal case. So really, let's do this. I mean, the ideal case, mu is in the row span of x. If it's not, let's take a look at the beta that makes it as close as possible. So find the beta that minimizes this norm and let epsilon be the vector that gives us the error. So epsilon is the part of mu that's not explained by the covariates. we can now compute the variance of tau hat. There's one term which is a quadratic form in Z, corresponding to the vector epsilon. There's a quadratic form in this matrix XCX transpose we were talking about, corresponding to the vector B, beta, and a cross term. And since we don't know anything about epsilon or beta, we're just going to upper bound these by, say, the 2 norm of Z times the norm squared of epsilon and the 2 norm of this other matrix times the norm squared of beta. If you think about it that way, it's clear that you want the 2 norm of Z to be small, and you want the 2 norm of XCX transpose to be small. So the IID design minimizes this. And as we'll see, the Gram-Schmidt Walk minimizes this. You really want to get both small. You can't minimize both simultaneously, but you can make a trade-off. So what we do in the Gram-Schmidt Walk design is we pick a trade-off parameter. We call it phi. It's a macro in the LaTeX file. We've gone through so many names, I don't know. Okay, it's phi in 0, 1. What we do is we run the Gram-Schmidt Walk algorithm. We're just going to get to use it, but not on the original covariates. We need to augment them first. So what we do is we stack a multiple of an elementary unit vector on top of them. So phi tells us how much we care about balancing Z versus XZX transpose. What we'll do is, well, okay, first, if the xi's were unit vectors, we put these multiples here so that we still get a unit vector out. So think if phi is equal to 1, this is just the elementary unit vectors. If you run the Gram-Schmidt Walk on the elementary unit vectors, you get the IID design. If we make phi equal to 0, we just run it on the covariates, but we want something in between. I should add one other thing we have to do is we have to randomly permute the order of the subjects before we run the Gram-Schmidt Walk design. That is not necessary for any of the purposes of BDGL, and it's actually not necessary for the tail bounds. What it's necessary for is for computing confidence intervals later, and I'll mention that at the end of the talk.
So then I have another question. Sorry for interrupting.
Oh, please.
How random are these? How random should I think of these Z's? Like, do they still take over? Like, are there their essential support still exponentially many points in the hypercube?
Yes.
Or are they very concentrated somewhere and so on?
So even if phi is equal to 0, the Z's are going to have exponential support, and there's a lot of it. And the bigger phi is, the closer phi is to 1, the higher the entropy of the support, or the higher the entropy of Z. So it'll still be very high entropy. I guess that's not a formal statement, that's an intuitive statement. I haven't checked. I think entropy is monotone in phi, but we have not checked. We tried, but we're not sure yet. There's a lot we don't understand about this. Okay, but you'll get some of that from the guarantees, because we're going to get some exponential concentration of tails, and you can only do that if you have very large support. Okay, so here are the guarantees we get. We get that this matrix Z, the expectation of ZZ transpose, is at most phi times the identity plus 1 minus phi x transpose x. So this is an n by n matrix. This is the Gram matrix of the covariates, the matrix of all outer product. It's at most this inverse. So that is the guarantee we get plugging into the guarantees we got from the Gram-Schmidt Walk. So to see implications of this, so first it tells us Z is at most 1 over phi times the identity. So the 2 norm of Z is at most 1 over phi. With a little more work, you can show that the 2 norm of XCX transpose is at most 1 over 1 minus phi. So this is the trade-off. I said that I want both of these matrices to have small norm. You can prove lower bound saying you just can't hope for that, but you can get any point along this curve. And that's what phi lets you select. Now, of course, I really should put back in the cross terms. If I put back in the cross terms, we actually get a nice formula for the variance of tau hat. What it looks like, so this you should see identify as a ridge regression. What it looks like is it's 1 over n squared times the minimum over beta of, here we have the distance from mu from x transpose beta squared. So that's really like, how close is mu to the row span of x, but normalized by a penalty on the norm of beta squared. And there's a 1 over phi here and a 1 over 1 minus phi here. So this is the bound we get for the variance. And we prove the corresponding sub-Gaussian tails. So it acts like a Gaussian with this as the variance. So we'll just say a little bit about what this all means now. So first, what I care about is if phi is more than a half. This means this is always at most 2. I should remind you this norm is always at most 1. That's what you get in the IID case. That's very important to me. I want to be able to tell experimenters that if they use this design, it can never, even if all of our assumptions fail and the covariates are completely useless, the variance can never be much worse than what you have in the IID design. Actually, I think in many cases, you're going to want to make phi pretty darn close to 1. Because, well, if say you assume any reasonable model, and all of this so far has sort of been model free for what the potential outcomes are. But if you assume a model for the potential outcomes, if you increase the number of experimental subjects, the optimal choice for phi grows closer to 1. I can imagine that if you were in a case where you really, sorry, let me cut down on some noise here. That helps. Okay, I can imagine that if you're in a case where you actually expect the covariates to be highly predictive, like this should be really small, you might want to let phi go pretty small, but I still can't imagine letting it go, say, less than 1/10. Because there is some downside if your assumption is wrong, how much, your variance could blow up a lot, and we don't want that. Okay, so now what I would like to do is tell you about the Gram-Schmidt Walk algorithm, which is a very beautiful thing, and tell you a little bit about how it works. It is a good time for me to pause for questions before I tell you what this algorithm does.
I have another question on the same thing. Just I'm trying to get to make sure I understand the intuition. So if all I'm asking, if I formulate all my requests in terms of variance, then I could get away with probably very small support. Yes. Right, so really I shouldn't just think about variance, right? Because right. So like pairwise independence or something like this would be enough, no?
You're right, pairwise independence would be enough. Not that we know how to do it any way other than this algorithm. I mean, I will tell you that, yeah, we spent quite a while trying to design other algorithms for this problem. And to actually get the variance down to 1, we couldn't for a long time. And then we realized maybe the right thing to do was reanalyze this algorithm. And again, why do I care about the variance more really being 1? Because I want to say that they can never be much worse than the IID design. So that's the term here. If I were to lose a factor here automatically, like using the analysis of BDGL, which was root 40, that would actually correspond to an increase of a factor of 40 of the number of experimental subjects we need to get a given level of error. So we were not comfortable with that. But yeah, we started out just thinking about the variance, not thinking about the tail bounds. And we don't know, if you come up with anything else that gets variance 1, we'd be very happy. There are some features that the Gram-Schmidt Walk doesn't have that we want. So we want other algorithms. But yes, you could get small support if you just cared about variance. When we get variance, that's sort of the language I will use to then introduce the sub-Gaussian concept.
Thanks.
Okay, so here's what the Gram-Schmidt Walk algorithm does. Remember, its input is vectors xi, of norm at most 1. We want to generate a vector z in plus minus 1. We're going to iteratively modify z. We start with z at the all 0 vector. During the course of the algorithm, I promise you that z will always lie inside the plus minus 1 hypercube, continuous. So the variables will always have values between -1 and 1. It's iterative. At every iteration, we will set some variable to 1 or -1, and the others will just vary inside the hypercube. So it's a loop. I describe it crudely here. While there is some I, such that z of I is not plus or -1, we're going to do an update on z, which is described by computing an update vector u, and then multiplying it by some random number delta. I'll tell you the distribution. And then we add z plus delta u. The key point is the expectation of delta is 0. So an expectation, z is going to remain all 0. We'll guarantee that when we do this, we fix one coordinate to plus -1. The others all stay in the range of -1 to 1. And at least here's an idea. Ideally, we would like xu, the update, to be orthogonal to xz. So we're somehow taking an orthogonal step to what we had before. If you're going to achieve that, you really need to assume that the xi's are independent, which means you assume the dimension is at least n. And I know that's not the intuition I gave you at first. But once we do the augmented covariates and I have those elementary unit vectors up top, all of the vectors are independent. Okay, let me drill in with a little more detail. The algorithm calls any variable that's at 1 or -1 frozen. And once a variable hits 1 or -1, it stays at that value. It will not change. The other entries we refer to as active. So we begin with everything active because they all start at 0. At every iteration, there's an element we call the pivot, a coordinate, and that's really the one we're going to try to fix, but we might not succeed. We're going to try to fix it at 1 or -1. So here's how we choose the update direction. We choose a vector u such that at the pivot, it is 1. It's 0 for every frozen coordinate, so those are not going to change. And we require that x times u be orthogonal to all of the xi's that are active, other than, of course, the pivot. This is n constraints on n variables. It has a unique solution, and you can show there is one. So this is a set of linear equations that we use to choose u. Then we update z by adding to it something times u, where that something is expectation 0. I will tell you exactly how we do that in a moment, but that guarantees the way we do it. We fix one coordinate to plus or -1 and the rest saying 1 -1. Then we update the active set. So that is the Gram-Schmidt Walk algorithm. Oh, I forgot to tell you how we choose delta. Well, there's only one way to choose delta, given what I told you. Let capital delta be the set of little deltas in which, when I take z plus delta u, it remains in plus -1. Now let delta plus be the max. If I set delta equal to delta, the max value in here, then some coordinate has to land, new coordinate has to land at 1 -1, because that's the boundary. Similarly, we let delta minus be, well, it's minus the minimum. If I set delta to minus delta minus, that's the other extreme here, so something has to land at plus -1. So we find what are the extremes we can set delta plus and delta minus, or delta to, and still land in the hypercube. We're going to choose one of those two values, and we just choose them with the probabilities that makes the expectation 0. So we update u by adding z by adding a expectation 0 delta times u. And then I got to put some indices on everything if I'm going to reason about the algorithm. So, okay, I will just tell you a few basic properties of the algorithm. We won't get too far into the analysis. First, if the vectors are in general position, then, and let's assume that, then one entry is frozen in every single step. Every step, something will turn to 1 or -1. Then there are going to be n steps. We can write then Zn as the vector we get out at the end. It is a sum of delta 1 times u1 through delta n times un. This is a martingale. Once you know delta 1 through delta t minus 1, the update vector ut is fixed, as is the distribution on delta t. And the expectation of delta t given those is 0. Using this, you can say the expectation of z at the end is 0. This is actually how I know that each entry will be plus or minus 1 with probability 1/2. We know we stop when z is a plus minus 1 vector. And we know that the expectation of z is the all 0 vector. That actually is enough to know each coordinate has to be plus or minus 1 with probability 1/2, just not independently. One other thing I will mention is, well, let me give you more of an explanation of how ut comes from. Ut is determined by delta 1 through delta t minus 1. Here's a way of describing it. The update vector is chosen so that x times ut is the projection of the pivot of the vector x, that is the covariate vector corresponding to the pivot, orthogonal to the xi's that are still active. So it's a projection orthogonal. Really all I want to use for now is that decreases the norm. Projections decrease norm. So here I'll at least give you some intuition for why we can get something 1 sub Gaussian out. The first is that we're writing z as a sum of these delta i's times ui's, I want to establish that the deltas, at least their squares, have small expectation. So let's say if p is the pivot, we're setting ut of p to be 1, but at the end of the step, zt can be, it has to remain within like 1 or minus 1. That gives us a bound on how big delta can be. We learned that delta t, we have an upper bound on it and a lower bound on it, and those differ by at most 2. So we're choosing delta t to be between one of two values that differ by at most 2, and the expectation is 0. That implies that the expectation of delta t squared is at most 1. That is part of why this sum can have variance 1, or be, the expected covariance 1, because each of the delta t squareds is expectation of most 1. I should also mention, this also tells us that each delta t individually, is a 1 sub-Gaussian random variable. This is what's called Hufting's lemma, which is one of the things we learned once when proving Hufting's theorem. So we get that each delta t is a 1 sub-Gaussian random variable. If, let's say, you knew that all the ui's were orthogonal vectors, that would be enough to prove everything we want. It's not necessarily the case. I will skip further analysis because I realize I will run out of time if I do too much of it. Let me just tell you what is the main difficulty one faces in the analysis. The pivot element might not be frozen. So we'd like the pivot element to be frozen, but that's not necessary. What is important, and what BDGL realizes, is that if the pivot is not frozen, it has to stay the pivot. This is why they set P to be the maximum active element. If something else is frozen, it's removed from the set of active elements, but then the maximum of them still remains the same if it wasn't P. Then you have to take a look at phases where the same element is pivot. And that's where all the complications come from. And that's where we needed a different way of proving sub-Gaussian concentration inequalities. Okay, so here are two natural questions. One is, can you improve the Gram-Schmidt Walk algorithm? And can you improve the design? There's not much room to improve the Gram-Schmidt Walk algorithm, at least for its own applications. So again, let's just take a look at variance for now. We said the operator norm, or largest eigenvalue, of the expectation over xz times its transpose is at most 1. That's the guarantee we get. Well, that implies that the trace of this expectation is at most d, because it's a d by d matrix. All the eigenvalues are at most 1. That's the norm of xz squared. So it says the expectation of the norm of xz squared is at most d. So there are cases you can't improve that. For example, what if x is the identity matrix? If x is the identity matrix, z is a plus minus 1 vector, this is going to have norm squared d. You can't improve that. If you're not satisfied with that example, if you want something of smaller dimension, just make x actually the horizontal concatenation of the identity with itself an odd number of times. And if after the talk you sit and think for a few minutes, you will realize that you still can't improve on this bound d in that case. Just because an odd number of 1s and minus 1s can't add to 0. Of course, you might wonder, okay, I told you there are matrices X on which you can't do better, but what if there is a matrix X on which you can? Could you tell? Well, the result of Charikar, Newman, and Nikolov tells us that's going to be hard. So they tell us that it's NP hard to distinguish between two situations. One in which there is a plus minus 1 vector z, such that xz is actually just the 0 vector. That would be really low variance. It's hard to distinguish that from the case in which the 2 norm of xz squared has to be at least some constant times d for every vector z. I don't know what that constant is, but at least up to that constant, it is going to be very hard to improve on the Gram-Schmidt Walk algorithm. Because hey, it's NP hard just to distinguish whether we could get this down to 0 or c times d. Okay, here's we should be able to make improvements. That's confidence intervals. Okay, so in the end, what we want is not just an estimator of low variance. We want an estimate of the standard deviation or the variance of our estimator. Here's how we're going to get an upper bound on that. Remember, we proved that n squared times the variance is the most a quadratic form, and this we called mu, which was the sum of the potential outcomes. And there's some matrix here I'm going to call Q. So really, to estimate the variance or upper bound, we would like to estimate mu transpose q mu, which I will expand into A transpose QA, B transpose QB, and a cross term. The question is, can we estimate that? And almost using a Horowitz-Thompson estimator. I mean, let's take a look at A transpose QA. This looks like we can estimate it. It's a sum. We don't observe all the terms, but we'll use a Horowitz-Thompson estimator and just take the sum over the i's and j's in A and divide by the probability that I and j are in A when we observe them. And you can think about doing the same for the cross term, but here there is an obvious problem. In the cross terms, I have down bottom somewhere the probability that I is in A and j is in B. And that's obviously a problem if I is equal to j. Because it is never the case that I is in A and I is in B. In that case, this probability is 0. And that's bad because I still want this term to estimate the variance. So there's a solution to this that Frederick tells me goes back to a 1923 paper of Nyman, which says, take a look at the diagonal of the matrix Q. That's where the problem that I just identified came from, right? These are diagonal entries because it's a problem in I is equal to j. Basically, you can use Cauchy-Schwarz and say that this term that we care about estimating is at most this term where I've moved the diagonal into the terms with A and B and subtracted it from the cross terms. So you can get an upper bound. And this you can try to estimate using a Horowitz-Thompson estimator. And I'd like to say you can, but there's one catch. I told you earlier, I glossed over that we do need all of these pairwise inclusion probabilities. We need them all to be greater than 0. I showed you one which had to be 0, which was when I was equal to j. But the others could be 0. In fact, if you look at the Gram-Schmidt Walk design, some of them can be. Like we've built examples where they are. The way we get around this is very crude and not sufficient yet. We randomly permute the vectors. And if we randomly permute the vectors, we can then show us a very crude bound, which is all these numbers are at least 1 in 4n times the minimum of this term, depending on our parameter phi. It's an unfortunate I'm at the 1 and 4n, and what does the 4n get you? Well, that then impacts the variance of our estimator of the variance. So we want something better. Okay, so let me just tell you another way we would like to improve this. Right now we are using this upper bound that we proved on the variance, but that's sort of loose. I mean, we can actually estimate that matrix Z that I gave you and figure it out, like, what is the expectation of ZZ transpose? And it's often much less than this upper bound that we prove. And when it is, we know, because I can estimate this matrix, I know the variance. But I want my sub-Gaussian bounds to depend upon the actual variance, and right now they don't. Right now they just depend on the upper bound. Why do I care? This can be another factor of 2. And a factor of 2 is a factor of 2 in the number of subjects you need to get that degree of confidence. So it would be nice to improve on this. By the way, let me add, you are free to use as much computation as you want. People are spending an insane amount of money on these studies. They will link at $10,000 of Amazon EC2 credits to grind out your sub-Gaussian constant. Okay, so what do we want to do in the end? Basically, this all said we want better tail bounds. I see I'm coming to the end. So let me mention one of the biggest problems left, an online version of this. In a lot of studies, you don't know all the subjects in advance, in which case you'd like to figure out who to assign to treatment and control as you go. There's really very little good to say about that problem right now, other than IID design. In practice, if you want to choose a design, you can, if you know all the covariates, do a lot of simulation for any design scheme you want and figure out what is that matrix Z. So you can do a lot of simulation, a lot of sampling to pick which design you want. You don't have to use the raw covariates. You can take functions of the covariates. You can take polynomial functions of the covariates. There's a lot you can throw into things like this. You can weight the covariates. If you think some are more important than others, just multiply them by weights and the design will emphasize different ones differently. One question I get a lot is, should we contemplate using machine learning or some sort of regression or something to adjust our estimates of tau hat based on the covariates? And I mentioned that we're sort of already doing something like that by design. Our variance estimator has a ridge regression baked in, except we're not actually doing the ridge regression. The outcome of the ridge regression just tells you what is the error of this naive simple estimator we're using. And I am much more comfortable doing that than using some sort of regression or machine learning black box to adjust tau hat, because if your assumptions are wrong, you can be fitting to noise, and that can really blow up your variance. And remember here, we want n to be small, or at least as small as possible. Okay, so if you want to learn more, this is our paper on arXiv. I'll mention there are two versions. The first version we put on in November was really geared towards a computer science style audience. The one we submitted is geared more towards experimentalists and statisticians. It has a different exposition. Some people will prefer the first one, but it does have more results and different simulations. And we have packages in Julia and R that people can use that are on GitHub. You could say find on my webpage. And there's a lot of this that didn't even make it into the 130 pages of the paper. So I think we're going to explain a lot of other stuff on some blog posts. Thank you.
Thanks so much. This is a mode in which not everyone can clap, but we can. So yeah, so we have now time for a Q&A. So if you have questions, please send them on the Q&A, and me and the other panelists will go through them. So we'll take a couple of, let's take a minute to gather some questions and so on.
Sure.
I guess we should also stop the recording.
Oh,
Ryan,
okay, sure. Yeah.